So I'm going to be talking about the Hess's Law today and what are the skills you need to know in order to interpret Hess's Law. First, you need to know how the change in enthalpy is changed when an equation changes, how to interpret Hess's Law, apply the principle of conservation, and sketch an energy diagram. Also, how to use it and explain Hess's Law. Who is Hess? Well, Henry Hess is a German scientist known for his thermochemical studies. Heat observed in a chemical reaction process is the same whether the process takes place in one or several steps. That was his concept. So, what is Hess's Law? Well, it's the principle of conservation of energy. Yeah, it's a kind of a mouthful now, but in a few minutes you'll get what it means. The amount of energy only depends on the states of a reactant and the state of its product, but not on the intermediate steps. Energy or enthalpy changes in chemical reaction are the same regardless if the steps occur in one or several steps. The total energy of a reaction is the sum of its total energy change in its many steps added together to total a reaction. So, we should always start with an example. So first thing you need to understand before you see an example is how to treat chemical reactions like a math equation. Well, you treat it like a math equation. That's the concept. So first, for example, when you multiply one side of the equation, either the reactant side or the product side, you must multiply the entire equation by the same number. So for instance, if you multiply 2 times x plus 1, you get 2x plus 1. When the necessary changes are needed to be made by flipping the chemical equation, the energy must be multiplied by a negative 1 number. So, like in a math equation, when negative 1 is multiplied by x plus 1, you get negative x minus 1. And finally, when you multiply an equation by a number, you must also multiply the energy or enthalpy by the same number. Okay, let's get into examples now. So, this is our example. 2 carbon equals hydrogen and ethylene. So, given all these three equations, what you need to do first is pinpoint all the compounds and elements given in the equation and in the given equations. So, like this. These three are the given ones that you have to get with the final equation. So you have to look at this and you know that it's on the wrong side. Not the wrong side, but the other side. So ethylene is on the other side of the equation. So in order to make it go to the product side, you need to flip the entire equation. And these are the reactant and product side. So what you need to do is flip. And remember, when you flip, you have to multiply the energy by negative 1. Therefore, when you flip, you get the first equation becomes plus 1299.5 kilojoules. And then you have ethylene on the right side. So after that, what is left is the second equation given. And you see that there's 2 carbon in the final equation and there's only 1 in the given one. Therefore, you must multiply the entire equation by 2. And when you do that, you get negative 787 kilojoules. And then you look at hydrogen, and hydrogen is already balanced. Therefore, you have your final answer. And then you have to cross it all out. You see 2 carbons, you cancel it out since they're on either side of the equation. And then you see 2 waters, you cross it out. And then you look at oxygen. Oxygen looks difficult, but when you look at the other side of the reaction, you see 2 plus 2.5 equals 5 over 2, which is 2.5. Therefore, they cancel out. And then you're left with the given equation. All you have to do is add them all up, and then you get your final enthalpy. Now, what does an endothermic reaction diagram look like? Well, you see the activation energy, and you see the reactant side and the product side, and the energy is absorbed since it's an endothermic reaction, and the products and the reactants difference is the delta H, which is the enthalpy. And these are the products. Okay, now this is another example. So this is quite simple. As you can see, all you need to do is cross them out, add them together, and then you get a negative number, which means it's an exothermic reaction. And an exothermic reaction diagram looks like this. The reactants often have more energy than the products, and energy is released